You're in a system design interview, and they hit you with it. Design Twitter. Your mind goes blank. Where do you even start? It's huge, right? Well, what if I told you there's a secret weapon, a skill that lets you slice through all that complexity and sketch out a solid plan in just a few minutes? That's exactly what back-of-the-envelope estimation is, and today we're jumping right in.
So, here's the game plan. First, we'll look at the estimation challenge itself. Then, we'll gear up with an essential estimation toolkit. After that, we're going to get our hands dirty and actually estimate Twitter. And finally, I'll give you some pro tips on how to nail your own calculations.
All right, let's dive into the challenge. You get asked to design some massive system, and your mind just races. How many servers do I need? 100? A million? How much storage are we talking about? You could just guess, but that's a surefire way to fail. What you really need is a framework, a structured approach to make estimates that you can actually stand by.
And look, this isn't just some clever trick for interviews. This quote here is from Jeff Dean. Yeah, Jeff Dean, from Google. He talks about this as a fundamental part of being an engineer. It's all about using your brain, thought experiments, and a handful of common numbers to get a quick gut check. It tells you if your design is even in the right ballpark. It's really about being approximately right, which is so much better than being precisely wrong. So, to boil it all down, what are we really doing here? We're just making some quick, rough calculations. The point isn't to get the exact number. No way. The goal is to understand the sheer scale of what we're building. Are we dealing with a bicycle or a freight train? Are we talking about a handful of gigabytes, or are we deep into petabyte territory? This gives you that all-important sense of scale right from the get-go.
Okay, so how do we actually do this? Well, you need a toolkit. Just like a chef has their favorite knives or a mechanic has their go-to wrenches, a system designer needs a few essential numbers memorized. We're talking numbers you should know cold. So let's open up that toolbox and see what's inside.
It really comes down to just 3 core tools. First, powers of 2, so we can talk about data size. Second, latency numbers, so we understand speed. And third, availability numbers, which is all about reliability. Master these 3, and you're well on your way.
First up, powers of 2. You have to speak the language of data fluently. You've got to know instinctively that a kilobyte is 1,000 bytes, a megabyte is 1,000,000, a gigabyte is 1,000,000,000. You get the picture. And this isn't just trivia. When you're planning for storage, mixing up a terabyte and a petabyte, well, that's 1,000 times difference. That's a mistake you just can't afford to make. All right, next tool in the box, latency. And I got to tell you, this is where your brain might start to melt a little bit. The difference in speed between different parts of a computer is just staggering. It's almost impossible to wrap your head around. So let's try to get a real feel for what fast and slow actually mean in a machine.
Okay, let's set our baseline. The fastest thing a computer can do is grab something from its L1 cache, right on the CPU. How fast is that? About 1 nanosecond. 1 billionth of a second. To a human, that's basically 0. It's our instant. Remember that number, 1 nanosecond.
Okay, you got that? 1 nanosecond. Now, what if we need to get that same piece of data from an old-school spinning hard drive? Brace yourself. That takes 1,000,000 nanoseconds. That is not a typo. It's 1,000,000 times slower. Why the huge difference? Well, the cache is all silicon and electricity. It's pure speed. But the hard drive? It's a physical thing. A little arm has to literally move across a spinning metal disk to find your data. And in the world of computing, any physical movement, that's an eternity. So what's the big takeaway here? It's simple, but it's one of the most important rules in system design. Memory is fast. Disk is slow, like really slow. If you're building something that needs to be fast, your main mission in life is to avoid disk seeks at all costs. It's the same reason we compress data before shooting it over the internet. Networks are slow compared to memory, so we want to send as little as possible.
Okay, our last tool, availability. You'll hear people talk about 9s of uptime. 3 nines, or 99.9% uptime sounds amazing, doesn't it? But think about what that actually means. It means your system can be down for almost 9 hours over the course of a year. That's a full workday. Now look what happens when we add just one more 9, 99.99%. Suddenly that downtime drops to less than an hour for the entire year. See? Every single line you add is a huge deal.
All right. Toolkit assembled. We've got our powers of 2 for size, our latency numbers for speed, and our availability 9s for reliability. Now for the really fun part. Let's take this shiny new toolkit and put it to work on a real problem. Let's try to figure out the scale of something massive, like Twitter.
So imagine you're in the hot seat.
The interviewer leans in and says, design Twitter. First thing to remember, don't panic. And definitely don't just start throwing numbers around. The very first, most critical step is to ask questions and make some assumptions. We need to put some boundaries around this huge, vague problem.
The key here is to state your assumptions out loud. It shows you're thinking methodically. So let's lay some down. We'll say 300 million monthly active users. Let's figure half of them use it daily. And each of those daily users post, say, 2 tweets a day. Maybe 10% of those tweets have a picture or video. And we'll decide to keep all this data for 5 years. Are these numbers perfectly accurate? Probably not, but it doesn't matter. What matters is that we have a reasonable common ground to start our calculations from.
Okay, let's start with the right traffic. How many new tweets are we getting? We'll use a common metric here called QPS, or queries per second. So, let's do the math step by step. We start with our 300 million monthly users, and half of them are daily, so that's 150 million daily active users. They each post 2 tweets, right? So, 150 million times 2, that's 300 million new tweets every single day. Now, how many seconds in a day? It's about 86,400. So we take our 300 million tweets and divide by 86,400 seconds, and that gets us to right around 3,500 tweets per second. That's our average.
But here's a critical detail. You never, ever design for the average. Traffic on the internet is spiky. It's like building a highway. You don't build it for 3 a.m. on a Tuesday. You build it for 5 p.m. on a Friday. For web services, a really good rule of thumb is to assume your peak traffic is at least double your average. So that 3,500 QPS we just calculated, we need to double it. We need to build a system that can handle 7,000 writes per second minimum, or it's going to fall over during the Super Bowl.
All right, next big question, storage. How much space do we need? Let's be smart about this and focus on the big stuff, which is media, pictures, and videos. Text is tiny. We can almost ignore it for a rough estimate. So we had 300 million tweets per day. Our assumption was that 10% have media. That's 30 million media uploads a day. If we guess an average size of, say, 1 megabyte per photo or video, that means we're adding 30 terabytes of new data every single day. That's a lot. Now let's see what that looks like over time.
So you take those 30 terabytes a day, you multiply it by 365 days in a year, and then you multiply that by the 5 years we need to store it, and you end up with roughly 55 petabytes. Let that sink in. A petabyte is 1,000 terabytes. That is an absolutely colossal amount of data. And that right there is why we do this. We just went from a fuzzy question, design Twitter, to a very real, very concrete number. We now know we need to build a system that can handle 55 petabytes of data. The problem just got a lot clearer.
So you've seen the whole process in action. You take a big problem, apply the tools from your kit, state your assumptions clearly, and then just walk through the math. It's a system. But now, let's talk about a few final tips that'll take you from just being able to do this to really mastering it.
Okay, here are your pro tips. Number 1, round your numbers. Don't try to calculate 86,400 seconds. Just use 86,000 or even 90,000. This is about getting in the right ballpark fast. Second, write everything down, especially your assumptions. It lets the other person follow your train of thought. Third, and this is a big one, label your units. Is that number kilobytes or kilobits? Megabytes or gigabytes? Getting that wrong can throw your whole estimate off by orders of magnitude. And finally, just practice. Do this for YouTube, for Instagram, for any app you use. The more you do it, the more natural it becomes.
And that's really all there is to it. Back-of-the-envelope estimation isn't some dark art. It's just a structured way of thinking that takes a scary, overwhelming problem and makes it something you can actually wrap your head around. It truly is your secret weapon for system design. So now that you have the tools, what are you going to break down next? Think about it. What's the scale of Netflix or Uber? The world is full of fascinating systems just waiting to be estimated.